Yes. Okay. So Tim basically asked me to talk about Life Paper 6, which is a paper that we published about 2 years ago now, and which specifically looks at life's capabilities to detect rocky planets in the habitable zones of sun-like stars. So yeah, I can also introduce myself briefly because I haven't been in the Life Team 2 meeting recently. Unfortunately, it's been a long time since I joined. But yeah, I'm a fellow at ESO at the moment, working on high contrast imaging of exoplanets, specifically also with interferometry using gravity. Before I was a postdoc at Space Telescope working on JWST, also among others, the JWST aperture masking interferometry mode. And together with Adrian and Andrea, I'm one of the team 3 lads of the instrument science team. So the things that we're doing there is mostly focusing now on deriving science and mission requirements, which are done by Adrian and Andrea mostly. But we're also developing simulator tools. So this is the life simulation tool, for instance, that many of you I have already heard are using. We're looking into signal processing techniques, and we're also doing yield estimates. So we're trying to estimate how many planets life could find and characterize. And this will also be the topic of today's talk and this paper that we have published here 2 years ago. So I'm hoping that most of you are familiar with the baseline concept that we have for life. It's basically this array of 4 telescopes that we sometimes call the X array, which is coming from some heritage based on the Darwin mission. And so the idea is basically to have a double Bracewell interferometer. But of course, we have also been studying different mission architectures, for instance, with either 3 or 5 telescopes, and then also having different beam combination schemes. But for now and for the rest of this paper and talk, we have been assuming this baseline design, which is simply 4 telescopes in this X-like configuration. Yeah, so here's mission parameters that are also the baseline values that you get if you're using LiveSim, basically. So as you might know, if you have used the tool before, there's 3 different... Can you see my pointer, by the way?
Yes, we can see it.
Okay, yeah. So you have 3 different scenarios. There's a pessimistic reference and an optimistic scenario. They have different primary mirror sizes and different wavelength ranges that they're considering. And these are the ones that we are exploring also in our paper here. The spectral resolution is kept at 20 for this work. And then we have the nulling baseline adjustable between 10 and 100 meters, so that depending on which system we are looking at, we can actually optimize the array for the separations of the habitable zone around this star. And we're also taking into account a couple of other parameters like detector quantum efficiency and total throughput and so on and so forth. But basically the most important one here is that we simulate a search phase of about 2.5 years. So the idea that we have as a baseline for the live mission is basically to have first a search phase where the mission is searching for Earth-like planets in the habitable zone of stars. And then we have a second mission phase, the characterization phase, where the most promising of these targets will be followed up to actually search for some biosignatures in their atmospheres and to do a more detailed characterization. But in the first mission phase, we first have to find as many good targets as possible, basically. And we assume a search phase of 2.5 years for that. We also take into account some slew times, so basically some penalty from switching from one to another target and some observing overheads. And then we are approaching the task of deriving these exoplanet yields for life with the PPOP tool and with the LiveSim tool. So PPOP is a tool that allows you to generate some synthetic planet population. So basically you give it an input catalog of stars. So this would be, for instance, a catalog of stars within 20 parsec from the sun. And then you give it some planet occurrence rates, for instance, from the Kepler spacecraft, and it can create for you some synthetic universe with exoplanets around all of those stars. And then, of course, we use LiveSim to check whether these planets are detectable or not with life. So our first work basically goes back to really the beginnings of life when I did my master's thesis at ETH and started to work with Sasha on these yield estimates for life. So in our first paper, we basically did an even simpler thing. We just created these synthetic exoplanets and we checked which of them can be seen with life and which ones cannot be seen. We didn't even simulate a survey and took into account all slews and observing time of 2.5 years and so on. It was just which planets could life in principle see. And so this plot here is showing you the stars are here just sorted. So we had about 320 or 330 stars in this stellar catalog back at the time, sorting them by the planet yield. So the expected number of planets that life would find on average around these stars. As you can see, all of the best targets are M-dwarfs. And there's multiple reasons for that. The first one is that Kepler has basically been finding that rocky planets, small rocky planets, appear more common around M-dwarfs than around earlier type stars. Although this has been put a bit into question by more recent work, but I think it's still somewhat a result of the mission. And also there's simply many M-dwarfs in the solar neighborhood. And you have to keep in mind that life with this interferometric, very large baselines, basically, we can resolve pretty much everything, right? So planets in the habitable zone around M-dwarf is mostly not a problem for us. So we are not limited by resolution, but by sensitivity. And that simply means that the more nearby a target is, the more easy it is for us to observe it. And that's why also the most nearby M-dwarfs are these very high yield targets here. Then a more recent study, this is from Life Paper 1 by Sasha, where we actually had then this more sophisticated optimizer that found the best possible observing sequence to look at different targets within 2.5 years of time and so on and so forth. And if you simply optimize that for the maximum number of planets in the rocky empirical habitable zone, then as you can see, it's mostly focusing on detections around M-stars again, especially if you consider these potentially habitable planets. There were only about 4 or so that were about G and K stars. And so kind of just to give a bit of a motivation, I mean, now we already have some information from JWST, but before it was simply also thought that M-dwarfs are more active. They have lots of flares and activity. So it might be more difficult for planets around these stars to be habitable. And also the only example that we have in the solar system is around a sun-like star, not around an M-dwarf. So there's some case to look at main sequence FGK stars, basically. And recent results from JWST are also pointing a bit into that direction. There's been several observations of rocky planets in habitable zone, and so far the data seems to be consistent with no atmosphere, or basically simply bare rocks. And hopefully in a few years from now, we will have more confident results from these observations, but it's kind of giving us further fuel to look at the sun-like stars also with life. So for this work, we focus on 2 different stellar samples. I mean, they were all taken from the same star catalog, but we made 2 different cuts on this catalog. The one was for what we call the sun-like stars, and the other one simply for all the FGK-type stars. And the reason why we had some more specifically called sun-like stars, which is simply a tighter cut on effective temperatures, because of the planet occurrence rates that we have been using for these estimates, which is what I will be talking about on the next slide. Well, actually, I forgot to mention there's about 360 or so FGK-type stars, and a bit less than half of that sun-like stars in this catalog. So we have been using some new planet occurrence rate. If you compare this with the Life Paper 1, what is called Q21 here is Life Paper 1. The advantage of this new occurrence rates from Bryson is basically that they are covering the entire habitable zone around the earlier type stars, as you can see in this plot that's shown here, right? So you can see the conservative and the optimistic habitable zones. And then the planet occurrence from Life Paper 1 is only going up to here, basically. So if you have very early type stars, you're missing the outer edges of the habitable zone because the orbital periods that you're simulating are not large enough. But now with this new model from Bryson, you're actually covering all of that. And in this paper, they have also specifically been focusing on rocky planets around these sun-like stars. So they just looked at exactly this subset of stars in the Kepler database to derive some robust occurrence rates for this sample. You can here basically see how many planets on average we have in these different types of habitable zones that are usually sometimes defined in these papers looking into habitability. Later, there's a comparison also with some paper for reflected light missions. They are also using this case called the exo-Earth candidates, which also has some more tight cut on the radius constraint of the planet. Okay, so yeah, then we went ahead and we ran basically live sim through all of these planets. We simulated 1,000 randomly drawn universes to get some kind of statistical average. And then we computed how many exoplanets you would be able to find, right, for these different types of habitable zones. And so this, just to remind you, is with the reference scenario of 2 meters mirrors and about 5% total throughput for the instrument. I forgot to mention this before, so there's a hub2 min and a hub2 max scenario just to make things a bit more complicated. So this has to do with the way how you extrapolate the occurrence rates from the Kepler mission towards longer orbital periods. Because in the Kepler catalog, they basically give you detections up to about 500 days orbital period, and also an estimate of the detection completeness up to that period. And then after that, you have to assume some extrapolation. And so the hub2 min and the hub2 max are basically just the two most extreme extrapolations that you could think of. And so the reality must for sure lie somewhere between those two scenarios. So, but as you can also see, these error bars, just based on based on the planet occurrence rates, how many planets were found, it was not a lot of rocky planets in the habitable zone around these early type stars. You have actually pretty significant astrophysical uncertainties simply to this is always the case with these exoplanet yield estimates. So this is for the sun-like stars, and then for the FGK-type stars. So you can see we should find, depending on what we look at, so for the FGK-type stars, for instance, between 16 to 22 planets in this optimistic habitable zone. But of course, one of the main questions is how many planets do we actually want to find? And this is something that Sasha has been looking at also in the live paper that was submitted to ESA. And so here is basically a plot that just shows you if you do the live mission and you don't detect any habitable planet, how confident can you basically rule out the habitability fraction of the solar system, right? We have in a solar system, we have that 1 out of 2 planets in the habitable zone is actually habitable, right? It's the Earth. Mars is not. And to rule that fraction out at 5 sigma with no detection, we would want to look at about 30 planets or so in the habitable zone. So that basically shows that with our baseline design, and if we really only want to focus on FGK or even sun-like stars, that doesn't seem to be quite possible. The other thing that we can then do with these yield estimates is we can try to start deriving some mission requirements. So we can rerun all of those simulations, but keep changing, for example, the primary mirror diameters of our spacecraft. And then we can investigate how the yield actually depends on that. And that can kind of show us how big of a mirror would we actually need to detect about 30 planets or so. And it seems that we would do quite a bit better with this optimistic scenario that has 3.5 meter mirrors. But of course, keep in mind, that's not the only parameter that we can tune. There's also another important parameter, here, which is the total throughput of the instrument. And for now, we have been assuming 5% total throughput. Of course, you could imagine that this total throughput could be higher. For instance, at the LBTI, they're already achieving 10% throughput at a wavelength of 10 microns. So it's not completely out of question that this could also be feasible for life. And again, you can see if you increase the throughput to maybe 15 or even a bit more percent, then you could again find more planets that are closer to this number of about 30. So yeah, one quick note of caution is that once you get to these bigger telescopes, so just to explain, what it's showing you basically which of the stars the optimizer, the life sequence optimizer is looking at. So the gray ones are the stars in our catalog, and the colored ones are the ones that are actually observed. It's not all of them, of course. But the bigger the telescopes, the more stars can be observed. And at the 3.5 mirrors, you can see that it's already distance limited. So if our stellar sample would go to about, more than 20 parsec, maybe 30 or so, the yield would probably increase because we are here in a distance limited case. So this is just as a note of caution. And if you compare our yields with what has been found, for instance, for HWO, the reflected light missions, they anticipate about 6-meter primary mirror diameter, which gives them also around 20 to 25 or so exo-Earth candidates. So it's a bit more than we had been finding for life in our paper. So this was more like a 15 to 20 or so from the plots of before. But as you have to keep in mind that we are kind of distance limited, so we're missing out there. And the other thing, so I'm going to skip over this for time, that's not very interesting. The other thing that I want to mention also is that we have not included, for instance, revisits in our observing sequence yet. So we're just going to every target once, and then after a certain time, if it's not worth it to stay longer, we go to another target, but we never come back to the same target. And of course, you could imagine that after, for example, for the Earth-Sun system, after a quarter of a year, you would come back, and if a planet was just behind the star the first time you look, it would be at conjunction the next time. So you would have a high chance of finding a planet if you revisit the system. And so if you include these revisits, that can also give you another boost of about maybe 10, maybe even more percent in the planet yield, so that we are in the end ending up with quite similar numbers to what the reflected light missions have. If we can either increase the mirror size or have a somewhat higher total throughput, of course, ideally, we have both of them to achieve this goal. And I think with that, I'm already probably over the 10 minutes quite a bit. I'm just looking, it's already 15. So sorry for going over the time a bit, and I'm happy to take any questions.